Welcome to this coding walkthrough. Today, we'll be tackling problem number 1939, maximum number of words you can type. This problem challenges us to maximize the number of words from a given text that can be typed on a keyboard, considering certain restrictions. We'll explore different approaches to solve this step by step. Let's dive in. In this problem, we're tasked with determining the maximum number of words that can be typed given a specific constraint. You're provided with two inputs, a string called text and another string called broken letters. The text string contains words separated by single spaces, and the broken letters string represents the letters on a keyboard that are broken and can't be used for typing. The goal is to figure out how many words in the text can be typed without using any of the characters listed in broken letters. Words are defined as sequences of characters separated by spaces. If even one letter in a word is broken, that word cannot be typed. The output will be an integer representing the total number of words that can be successfully typed without using any of the broken letters. Let's look at an example to clarify. Suppose the input text is "Hello World," and the broken letters string is "add." The words in text are "hello" in world. The first word, "hello," does not contain the letters A or D, which are broken, so it can be typed. However, the second word, "world," contains the letter D, which is broken, so it cannot be typed. As a result, only one word can be typed, and the output is 1. Now, consider another example with text equal to LeetCode and broken letters equal to E. Here, the words in text are Leet and Code. Both of these words contain the letter E, which is listed as broken. Since neither word can be typed without using the broken letter E, the output is 0. On the other hand, if broken letters is an empty string, it means no letters are broken. In this case, both words Leet and Code can be typed, resulting in an output of 2. Finally, let's review the constraints and edge cases to keep in mind. The text string will always have a length between 1 and 10,000 characters, while the broken letters string can range from 0 to 26 characters. The words in text are separated by single spaces, and there are no leading or trailing spaces. Each word in text consists solely of lowercase English letters, and broken letters contains unique lowercase English letters. For edge cases, remember that if broken letters is empty, all words in text can be typed. If text is empty, the output should be 0. Similarly, if all the letters in text are broken, the output will also be 0. For single word inputs, ensure that the word is properly evaluated based on broken letters. Lastly, the solution must handle the maximum input size efficiently to meet performance requirements. To solve this problem, we considered a couple of approaches. The most straightforward method is the brute force approach. The idea here is to iterate through each word in the input text and check if any of its characters are present in the set of broken letters. If a word contains a broken letter, it cannot be typed, so we simply skip it. On the other hand, if no broken letters are found, we increment our count of typable words. The steps for this method are simple. First, split the text into individual words. Then, for each word, we check character by character against the broken letters. This approach, while intuitive, involves a lot of checks, especially as the size of the text grows. The time complexity is O, and *m, where n is the number of words and m is the average length of each word, and the space complexity is O, b, where b is the size of the broken letters set. To make this more efficient, we considered an optimized approach. In this version, instead of repeatedly checking characters against a list or string of broken letters, we pre-process the broken letters into a set. This allows for O1 lookups, significantly speeding up the process. The optimized approach is both efficient and straightforward. First, we convert the broken letters into a set, which ensures fast lookups whenever we need to check if a character is broken. Next, we split the input text into words, just like in the brute force method. Then, for each word, we iterate through its characters and check them against the broken letters set. If none of the characters are found in the set, the word is considered typable, and we increment the count. While this approach has the same time complexity, O, and *m, as the brute force method, the critical improvement comes from the O1 lookup time provided by the set. This makes the solution more scalable for larger inputs. Additionally, we explored an alternative approach using regular expressions. By leveraging regex, we can filter out words containing broken letters in a concise manner. However, regex introduces additional processing overhead and is generally less efficient compared to the optimized approach, especially for large-scale inputs. While regex can make the code shorter, it may not deliver the same level of performance as the manual set-based iteration. Among the approaches considered, the optimized strategy was chosen as the most effective solution. By converting the broken letters into a set, we greatly reduced the computational cost associated with redundant checks. This pre-processing step ensures that each lookup operation is fast and allows the algorithm to handle larger inputs efficiently. Additionally, the logic of processing the text word by word provides a clear structure to the solution. Each word is handled independently, which simplifies the implementation and makes it easier to understand. While the regex-based solution is elegant in its brevity, it introduces unnecessary complexity and overhead, which are not ideal for this problem. The key takeaway here is that pre-processing the broken letters into a set is a critical optimization, as it provides a significant performance boost without adding much complexity. Splitting the text into individual words complements this approach by creating a clean and efficient workflow for processing the input. When assessing the trade-offs between these approaches, the brute force method stands out for its simplicity, but it quickly becomes inefficient as the input size grows. The optimized approach, while slightly more complex, scales much better for larger data due to the use of a set for fast lookups. This makes it a robust solution that balances clarity, performance, and scalability. On the other hand, the regex-based approach, while concise, sacrifices performance for code brevity. Regular expressions can introduce processing overhead and are less intuitive to debug or optimize for this specific problem. Ultimately, the optimized approach strikes the best balance, combining the clarity of manual iteration with the efficiency of pre-processing. This makes it the most practical and effective strategy for solving the problem of determining the maximum number of words that can be typed given a set of broken letters. In this problem, we're tasked with identifying how many words from a given text string can be fully typed on a keyboard where certain keys are broken. A broken key means that any word containing this letter cannot be typed. Our inputs are a text string of words separated by spaces and a broken letters string, which lists the broken keys. The goal is to count the number of words in text that do not contain any of the broken letters. To achieve this, we start by splitting the text string into a list of words using the split function. This allows us to process each word individually. For example, if the text is Hello World, this becomes the list, Hello World. Next, we convert the broken letters string into a set of characters. Using a set allows us to perform fast lookups when we check if a letter is broken. For instance, if broken letters is add, the set becomes a D. Finally, we initialize a counter called typableCount to 0, which will keep track of how many words can be typed without using any broken letters. After pre-processing the input, we move on to processing each word. We start by looping through each word in the list created from the text string. For each word, we check whether it contains any characters that are broken. To do this efficiently, we use a flag called isTypable, which we initially set to true. Then, for each character in the word, we check if it exists in the set of broken letters. If we find a broken letter, we set the isTypable flag to false and break out of the loop for that word. This ensures that we don't waste time checking the remaining characters in the word once we know it can't be typed. If the isTypable flag remains true after checking all characters, we increment the typable count by 1. Once all words have been processed, the final value of typable count is returned as the result. This approach leverages the efficiency of set lookups and avoids unnecessary computations, making it both clear and performant. To further optimize the process, we use an early exit strategy. As soon as we find a broken letter in a word, we stop checking the remaining characters of that word. This saves computational time, especially for longer words. In terms of data structures, we use a set for broken letters because it provides fast O1 average time lookups. Additionally, we use a list to store the words from the text string, which makes it easy to iterate through them. Analyzing the time complexity, the algorithm runs in O, m plus n asterisk k, where m is the length of broken letters, to create the set, n is the number of words in the text string, and k is the average length of a word, to check each character. The space complexity is O, m plus n, due to the set of broken letters and the list of words. By structuring the algorithm this way, we ensure that it handles both small and large inputs efficiently. To illustrate how the algorithm works, let's walk through an example. Suppose the text is "Hello World" and the broken letters are "add." First, we split the text string into a list of words, resulting in "Hello World." Next, we convert broken letters into a set, giving us a D. We then initialize typable count to 0. Now, we process each word. For hello, we check each character, H, E, L, L, and O. None of these are in the broken letters set, so we increment typable count to 1. Moving on to world, we check W, O, R, and L. So far, none of these are broken. However, when we reach D, we find it in the broken letters set. This means world cannot be typed, so we don't increment the counter. After processing all words, the final value of typable count is 1. Now, let's consider some edge cases. If the text string is empty, or if broken letters is empty, the output will depend on the input. For an empty text, there are no words to process, so the result is 0. If broken letters is empty, then no letters are broken, and all words in the text string are typable. Another edge case is when all possible letters are broken. In this scenario, no word can be typed, so the result is 0. Additionally, we must handle special characters, such as punctuation, correctly. These should not interfere with the algorithm's ability to determine whether a word is typable. Overall, the algorithm is designed to handle these situations gracefully. Here is the Python implementation of the solution, which combines all the steps we've discussed. In the implementation, we define a function count_typable_ words that takes text and broken letters as inputs. The function splits the text into words, converts broken letters into a set, and initializes the typable count to 0. It then iterates through each word, checking its characters against the set of broken letters. If a word contains no broken letters, the counter is increment. Finally, the function returns the value of typable count. Using the example input of text equals "hello world" and broken letters equals "add," the function outputs 1, as only hello can be typed. This implementation is efficient, clear, and handles edge cases effectively, making it a robust solution to the problem. The given solution implements the problem of counting the maximum number of words that can be typed given some broken letters on a keyboard. Here's a detailed breakdown of the code. 1. Import in function setup. The solution class contains the can-be-typed words method, which takes 2 parameters, text, a string of words separated by spaces, and broken letters, a string containing the broken keys. 2. Convert broken letters to a set. The broken letters string is converted into a set called broken_set. This allows for fast O1 lookup when checking if a character is broken. Using a set is efficient because we need to repeatedly check if characters belong to the set. 3. Split text into words. The input text is split into a list of words using the split method. Each word will be processed individually to determine if it can be typed. 4. Initialize valid word counter. The valid_word_count variable is initialized to 0. This variable keeps track of the number of words that do not contain any broken letters. 5. Iterate through words. The code iterates through each word in the words list. For each word, it checks if all characters in the word are not in the broken_set. This is done using the all function combined with a generator expression that iterates over the characters of the word. 6. Update valid word count. If all characters in the word pass the check, i.e., none of them are in the broken_set, the word is considered valid, and valid_word_count is incremented by 1. 7. Return the result. After processing all the words, the method returns the total count of valid words stored in valid_word_count. ### example walkthrough. Input, text equals hello world, broken letters equals add. Broken_set becomes A, D. Words equals hello world. For hello, none of its characters are in A, D, so it is valid. For world, none of its characters are in A, D, so it is valid. Valid_word_count equals 2, which is returned. ### edge cases. If broken letters is empty, all words are valid. If text is empty, the result is 0. If all letters in text are broken, the result is 0. The algorithm is efficient with a time complexity of O, n asterisk m, where n is the number of words and m is the average length of each word. This ensures quick execution even for larger inputs. Here, we start by importing the necessary utilities and defining our solution class with the method CanBeTypedWords. The goal of this method is to determine how many words in the given text can be typed without using any of the broken letters. First, we take the broken letters string and convert it into a set of characters, called broken set. Using a set allows us to perform efficient lookups when checking if a letter is broken. Next, we split the input text into an array of words using the split method, where each word is separated by a space. We then initialize a counter, valid word count, to track the number of words that can be typed. After this, we enter a loop to iterate over each word in the array. Inside this loop, we assume initially that the word is valid by setting a Boolean flag, isValid, to true. For each character in the current word, we check if the character exists in the broken set. If it does, the word is invalid, so we set isValid to false and break out of the loop to stop further checks for that word. If the word passes all the character checks and remains valid, we increment the valid word count. This process continues for all the words in the input text. Finally, after evaluating all the words, we return the valid word count as the result. This value represents the total number of words that can be typed without using any of the broken letters. The implementation is efficient, leveraging a set for fast lookups and ensuring that we exit early from unnecessary checks whenever a broken letter is found in a word. To solve this problem, we start with the first example where the input text is Hello World and the broken letters are add. First, we convert the broken letters into a set for efficient lookups, resulting in broken_set being d. Next, we split the text into individual words, giving us the list, Hello World, and we initialize a counter valid_word_count to 0. Now, we process each word one by one. For the first word, hello, we check each letter to see if it exists in broken_set. None of the letters H, E, L, or O are found in the broken set, which means hello is a valid word. We increment the valid word count to 1. Now we move on to the second word, world. Again, we check each letter against the broken_set. The letters W, O, R, and L are not found in the broken set, but the letter D is. Since world contains a broken letter, it is not valid, and the count remains unchanged. At the end of this process, the total number of valid words is 1, and we return 1 as the final output for this example. In the second example, the text is LeetCode and the broken letters are E. As before, we start by converting the broken letters into a set, resulting in broken_set being E. The text is split into words, producing the list, LeetCode, and we initialize the valid_word_count to 0. For the first word, leet, we check each letter to see if it exists in the broken set. The letters L and T are not in the broken set, but E is. Since leet contains a broken letter, it is not valid, and the count remains at 0. Next, we process the second word, code. Checking each letter, we find that C, O, and D are not in the broken set, but E is. This means code also contains a broken letter, making it invalid. Since neither word in the text is valid, the valid_word_count remains 0. The final output for this example is 0, which we return. In the third example, the input text is apple, banana, orange, and the broken letters are XYZ. We convert the broken letters into a set, resulting in broken_set being X, Y, Z. Splitting the text gives us the words apple, banana, orange, and we initialize the valid_word_count to 0. Starting with the first word, apple, we check each letter against the broken set. None of the letters of P, L, E are found in the broken_set, so apple is a valid word. We increment the valid word count to 1. The second word is banana. Checking each letter, none of them B, N are found in the broken set. This means banana is also valid, and we increment the count to 2. Finally, we process the third word, orange. Again, none of its letters O, R, N, G, E are found in the broken set. Since all 3 words are valid, we increment the count to 3. The total number of valid words is 3, and we return 3 as the output for this example. In this analysis, we'll break down the time complexity step by step to understand how the solution performs. First, we convert the broken letters string into a set. This operation involves iterating through each character in the string and adding it to the set. If we let b represent the length of broken letters, this process takes b time. Next, we split the text string into words using the split function. Here, n represents the total length of the text, and the split function scans through the string once to identify the boundaries between words, which also takes n time. These two steps lay the groundwork for processing the input efficiently. Now, we move on to the step where we check the validity of each word. Let w represent the total number of words in text, and m be the average length of a word. For each word, the conditional char not in broken underscore set for char and word iterates through every character of the word to verify that none of them exist in broken underscore set. Membership checks in a set are, on average, 1, so validating a single word of length m takes m time. When we process all w words, this step requires w*m time. However, since the total length of all words combined equals the length of text, w*m simplifies to n. Therefore, this step has a time complexity of n. Adding everything together, we have b for creating the set, n for splitting the text, and n for validating the words. This gives us a final overall time complexity of b plus n. Let's now analyze the space complexity of the solution. First, the broken underscore set requires space to store all the unique characters from the broken letters string. Since there are b characters in broken letters, this step uses b space. Next, when the text string is split into words, a list is created to store these words. Assuming the total length of text is n, this list requires n space. For intermediate operations, the generator expression used to validate words operates lazily, meaning it does not allocate additional memory beyond 1. Similarly, variables like valid underscore word underscore count and other constants also use 1 space. Adding these contributions together, the space complexity is dominated by the broken underscore set in the words list, resulting in b plus n overall. When considering best, worst, and average cases, the operations remain consistent. In the best case, all words in text are valid, meaning none of their characters appear in broken letters. Even in this scenario, the algorithm still examines each character in text, leading to b plus n time complexity. In the worst case, no words are valid because every character in every word appears in broken letters. Despite this, the algorithm must still process all characters in text, so the time complexity remains b plus n. The average case is no different, as the algorithm does not optimize based on the distribution of valid or invalid words. Comparatively, a naive approach that checks each word character by character against the broken letters string would result in n*b time complexity. This is significantly less efficient than the optimized solution, which leverages the 1 membership checks of a set to achieve linear time complexity. Space complexity, at b plus n, is also optimal since storing the words list and broken underscore set is unavoidable in this problem. To summarize, the solution achieves a time complexity of b plus n, where b is the length of the broken letters string and n is the length of the text. The space complexity is also b plus n, accounting for the memory used by the broken underscore set and the list of words. By utilizing a set for efficient membership checks, the solution avoids the inefficiencies of a naive approach and processes the input in linear time. This combination of time and space efficiency makes the solution well suited for handling large inputs while maintaining clarity and simplicity. When solving this problem, there are several common mistakes to be aware of that can lead to inefficiencies or incorrect results. First, not handling edge cases like empty strings or inputs is a frequent oversight. If the text is empty, the expected result is usually 0, but failure to explicitly check for this might result in errors or unintended behavior, such as index out-of-bound issues. Another common mistake is having an inefficient implementation. For example, using nested loops to compare every character in each word with broken letters can result in n*m time complexity, which may cause time limit exceeded errors for large datasets. Instead, using a set for broken letters can significantly speed up lookups. Additionally, overlooking case sensitivity can lead to mismatched comparisons. If the problem is case-sensitive, your code should account for that, or if it's not, you'll need to normalize the case of the inputs by converting them to lowercase. Modifying the input data directly is another pitfall to avoid. If you alter the original text or broken letters, you might introduce bugs, especially if other parts of your code rely on the original data. Finally, incorrectly counting valid words happens often when flags used to determine whether a word is valid aren't reset properly for each word, leading to errors in the final result. Being mindful of these issues can help you avoid unnecessary debugging time and improve your overall solution quality. Now, when approaching this problem in an interview setting, there are some key strategies to keep in mind. First, always optimize for both readability and efficiency. It's okay to start with a brute force solution if you're unsure, but make sure to explain its limitations and how you'd refine it. This ability to identify trade-offs is something interviewers value highly. Also, think aloud as you work. For instance, you might explain why using a set for broken letters reduces the lookup time to 1, showcasing your understanding of time complexity. Asking clarifying questions is equally important. Confirm details like how to handle empty inputs, whether the problem is case-sensitive, and how exactly a broken word is defined. This demonstrates your attention to detail and ensures you're solving the right problem. Finally, highlight how your solution scales. If time allows, discuss how your approach would perform with large inputs and what further optimizations you might consider, such as balancing space and time complexity. For additional practice, you can explore related problems that build similar skills, such as LeetCode 1108, 929, 804, and 771. These problems will help reinforce your understanding of string manipulation and efficient lookups. There are also alternative approaches for solving this problem, each with its own trade-offs. One of the most efficient methods is set-based filtering. By converting broken letters into a set, you can achieve 1 lookups as you iterate through the words in text. For each word, you simply check if any of its characters exist in the set. This approach is both fast and straightforward, with a time complexity of n plus m, where n is the total number of characters in text and m is the length of broken letters. The trade-off here is a slight increase in space usage due to the set. Another approach is to use Python's built-in string methods, like the any function. This can make your code more concise, as it allows you to check for the presence of broken letters in a word with minimal lines of code. However, it may not be the most efficient method for very large inputs, so there's a trade-off between readability and performance. Finally, for advanced users, bit masking offers a highly efficient solution. By representing both broken letters and words as bit masks, you can use bitwise operations to check for overlapping characters. While this method is faster for large datasets, it's also more complex to implement and harder to debug, making it less intuitive for most developers. Choosing the right approach depends on the problem constraints and your own comfort level with these techniques. Great job! In this session, we covered the maximum number of words you can type problem, discussed the brute force approach, and analyzed the solution's complexity. Remember, building a strong problem-solving foundation is key to mastering coding challenges. Thank you for joining, and I'll see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!